Hey guys, today we'll talk about the real numbers. Well, the real numbers we have proved mathematically that they are complete, they are compact, they are connected. Uh, Whenever I see the new students in the class, I ask them a question that do you think that the number 2 is a real number? And I see some students, they get confused. And they get confused. There is only one reason that they are not familiar with the basic number system. So today I'm going to explain the basic number system with a history of numbers. If you have any questions, you can write in the comments, and I will do my best to answer those questions. Well, let's go back when we used to live in caves. At that time, keep in mind there were no shapes of numbers, which came later. But you can just imagine that those numbers, they look like dots, like these. And you can keep on going all the way to infinity. Well, how many numbers we have? We have infinite many numbers. Are they enough? Well, they are more than enough. With the passage of time, we learned that these numbers were not enough. So we learned that there should be some more numbers, and we call them negative numbers. And you can see that again, they look like some dots, and they go all the way to negative infinity. Well, if you see that the distance between 2 and 1 is 1 unit, between 3 and 2 is 1 unit, between -1 and -2 is 1 unit, -2 and -3 1 units, and you can proceed it the same way. But the distance between -1 and 1, that's 2 units. Okay, what does this mean? Because 1 minus -1 is 1 plus 1, which is 2. So it means that we are missing something here. This number right in the middle of -1 and 1. Now everybody knows that this number was 0. And then we got a complete set of numbers, and this set of numbers were called set of integers. Okay, so some books they write in the form of z, some books they call in the form of I. Okay, so how this set looks like is we have z, and we have 0, we have plus minus 1, plus minus 2, is going all the way to both the infinities, plus infinity and negative infinity. Well, again, with the passage of time, we learned that even these set of numbers, they were not enough. So some, they started thinking about what is between these numbers. Okay, for example, we can say that this point, we should have 1/2. Then exactly in the middle of these, we have 1/4, exactly in the middle, we have 1/8, and so on and so forth. So we learned that actually there are infinite many numbers between 0 and 1. Wow. So, well, now the question is, all these numbers, you can imagine here that they are getting closer and closer and closer to each other. Now, someone raised the question, are they going to touch each other? Are they going to fill the space between 0 and 1? By the way, these numbers with the fractions, they were named as set of quotients. Okay, we'll say Q. So in this set, now we have 0, we have plus minus 1/2, and all the fractions like these, we have plus minus 1, blah, 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 blah. We call them set of fractions. Well, the question is that, is the number 2 which is an integer, is a fraction? Well, the answer is yes, because we can write it in the form of 2 over 1, which is 2. And that's the definition of the fractions. They could be written in the form of p over q, where p and q are integers and q cannot be equal to 0. Okay, so we got some idea about the fractions. Then this question that all the integers, all the fractions, are they connected to each other or not? Well, that was a very reasonable question, and it took some time. And just imagine this triangle. We know that, okay, assume that this is the right triangle. And we have, just to make things simple, each side of length 1. Can you imagine that the most wise, there was a time when the most wise person, the most wise mathematician on the face of the earth was not able to calculate what is the hypotenuse value of this such a simple triangle. Okay, and the reason is that they were aware about the fractions, but they were not aware about these kind of numbers, which are not fraction. There is a very famous theorem which says that root 2 is not a fraction. Well, if root 2 is not a fraction, with simple analogy, we can say that since square root of 1 is 1 and square root of 4 is equal to 2, so we know that this guy, which is not a fraction, it should be between 1 and 2. Somewhere between 1 and 2. Well, now the question is, if between 1 and 2 there are only fractions, the numbers like these, how come the number like root 2 are going to be between them if they were connected with each other? So from there we learned that actually there was still some space between the fractions, and that space was filled with some other type of numbers, which we call them non-fractions. Okay, so a new set was established, which we call it, assume that this is q star, which contain the numbers like root 2, like pi, like e, like all those numbers which cannot be written in the form of fractions. This set was named the set of irrational numbers. Okay, and when we combine the rational and the irrational numbers, a new set was established, and that's what we are talking today, is called the set of real numbers. And this set is actually the union of the fractions and the non-fractions. So actually this set contains all kind of real numbers, all kind of fractions, all kinds of non-fractions, all kind of integers, and all kind of counting numbers. Okay, what does this mean? It means that is 2. Okay, there is actually even a more basic number, which is called a set of counting numbers. Another name for this set is a set of natural numbers. That's why we call it n. So this set actually is the most basic. So we see that 2 is a counting number. Why we call it counting number? Because that's the way we count. If I give you $5, $1 bill, and I ask you to count, you start with 1 and then 2 and then 3. You start with 1. We don't start with 0. We don't start with -1. Okay, it's going to mess up everything. So we start with 1, 2, 3, and that's the way we count. That's why it's called a set of counting numbers. So we know that 2 is a counting number. Well, we see that 2 is integer as well. And we learned that 2 is a fraction as well. And we learned that 2 is part of the real numbers as well. So it means that all the natural numbers, they are real. All the integers are real. All the fractions are real. All the non-fractions are real. And now we can draw a straight line. Before that, we had just dots, getting closer and closer and closer to each other. But now, with the real numbers, we prove that, we have mathematically proved that the set of real numbers, they are connected, they are complete. And what else we need? Okay. Let's see algebraically how we knew that there was a need of some more numbers. Okay, assume that we have let's go back again to the old times, and we say that the only numbers we knew were set of counting numbers, 1, 2, 3, all the way to infinity. Well, how many numbers we have? We have infinite many numbers. Now the question is, if I have some algebraic equation like x minus 2 is equal to 0, how can I solve it? Well, I will say that, well, that's the only collection I have, and among this collection there is a number 2 which I plug in here and it will satisfy this equation. And I say that, well, 2 minus 2 is equal to 0, so 2 is working. That's good. Is there any number in the whole infinite many counting numbers which I can plug in here and I get 0? No. That's the only one answer which can fulfill. Okay, so among all the infinite many numbers, there is only one answer which I can plug in. But just see, if I make a small change here and I say that, actually, what about if x plus 2 is equal to 0? Well, now I'm in trouble because none of these numbers can answer this question. So now I say that, well, these numbers are not enough to answer any kind of equation. So I jumped to, for example, another set, which is set of integers. I have 0, I have plus minus 1, I have plus minus 2. Okay, which is, you can see that, which has twice many numbers as set of counting numbers. But since we are dealing with infinite many numbers, okay, we will not say that, okay, this number has more number than the set of counting numbers. Okay, if they are infinite, we don't talk about cardinality. Okay, so I see that, well, I don't get any number from set of counting numbers, but there is a number in this set which, if I plug in here, is working. Okay, and that number is -2 plus 2 is equal to 0. Wow, now I'm happy that this set can answer the questions like this, and it can answer the question like this. Well, you don't have to be very happy. We have another equation like 2x minus 1 is equal to 0. Wow. Now the problem is there is no integer in this whole collection, infinite many numbers, which can fit here. So we say that, well, our space was set was still not enough. So we say that, hold on. Actually, we have established a new set which has all the fractions in all the integers, and now we can plug in a number. Okay, let's make it red. That we have a number which is 1/2, which we can plug in here, and we get 2 times 1/2 minus 1 equal to 0. It means that this is actually 1 minus 1 equal to 0, and 0 equal to 0. So it's working. So we say that, well, 1/2 is the solution of this equation. Well, we are happy again that now we can, and this set Q, it can answer the question like this, it can answer the question like this, and it can answer the question like this. Well, again, we are happy, and we thought we have done a big achievement. But let's see this equation. X squared minus 2 is equal to 0. Well, again, we cannot find any number in this set which is going to answer this question. So we got a new collection of sets which has all the non-fractions, pi, e, blah, 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 blah. So we figure out that actually there is a number. Let's find a different color. Okay, let's do, okay, red. This guy, if we plug in here, this is root 2 square minus 2, which is equal to 0. So this is actually 2 minus 2 equal to 0. So 0 is equal to 0. Well, it's working. It means that we can answer these questions. So when we combine these two sets into one set, which is called a set of real numbers, which has all the fractions and all the non-fractions, actually we have developed a set which can answer all the equations like these, these, and this one. So mathematically, actually, we proved that, just like I told you guys, that this set of real numbers is connected and is complete. So we were happy that we are done, we have a good job. But unfortunately, if I ask a question, x squared plus 1 is equal to 0, well, we cannot find any real number which could fit here, because in the space of real numbers this looks like a lie, because any number I plug in here, assume that I say that -1 is the solution, plus 1, this square is going to make it positive, and it's going to be 1 plus 1, and there is no way this is equal to 0. Actually, any negative number or positive number you plug in, this square is going to make it positive. And two positive, they never close to go to 0.